All right. So oh, maybe I should give it a little longer. So I'm tired because it's the end of the day, and I realize like you're doing this every day, right? So this is the day that I do two lectures, and you anyway. So what we're going to look at was the four-dimensional n equal one theory coupled to matter. And I felt I had to tell you this because it's kind of the basics of supergravity in four dimensions and phenomenology. So we have this chiral matter, and we're gonna have some number of them, some number of chiral multiplets, and they're kind of got. We can think of them as being a complex field, and we can think of this as living in some space x. So they're thinking of them as like coordinates in some space x, and they have a fermionic partner, and there's some gauge matter with I from 1 up to, I don't know, R, and they've got gauge fields with an index A, confusingly, and some spin half things. So let me tell you what the, and then we've got gravity, which is going to have G mu nu, GMN, the graviton and the gravitino. So let me tell you what the action looks like, and then we'll do some unpackaging of it. So let's look at the action and the chiral field geometry. So again, I'm going to write down a complicated action, and then I'm going to explain to you what the different bits are. So let's only do the bosonic fields. Okay. If I wrote down all the fermions, we'd be here for several weeks. Well, that's not quite true, but for a long time. And the interesting geometry is in the bosons. The fermions become naturally associated to things like tangent vectors, vector fields on the bosonic geometry, but let's not go there. So I have a four-dimensional action, and since I'm turning off all the fermions, I don't have to worry about the extra torsion terms and things. So this is just honestly the, this is honestly the Levi-Civita scalar curvature. And then I get, and I'll try and, this is supposed to be a curly G. Oh, that looks exactly like that G. All right, what should I call this? Let me call it G hat, I, J bar. And this is a function of the fields, and it controls the kinetic energy term of the fields. So that's a kinetic energy term of the fields, but it's not standard, right? It's got some extra dependence here. That's what's usually called a sigma model. And then there are some gauge field bits, and they depend on the real part of something. And then there's something that looks like the ordinary f squared, f mu nu squared, or fmn squared. And then there's another term which goes with the imaginary part of this function. And they come with ff dual, so they have mn fb pq, right? So this is like f squared, this is like f contracted with the dual f. If this term wasn't there, if this was a constant, this would be just a topological term. And then there's a potential. Yeah. These real and imaginary parts? Okay, so there's some, so FAB is a holomorphic function of the zi's. So you should just think of it as some FAB just depending on zi, it doesn't depend on the bar. And so since it's complex, I can take its real part and stick it here, and its imaginary part and stick it here. Okay. Say again? The z's are all complex things because they're chiral multiplets and they have a complex scalar and a chiral multiplet. Any other questions? Yeah. So you should think of it as like, going to look like a metric on this field space. So if I think of the z's as coordinates, this is like a metric on that space. So that's what I want to... So, you know, if you were writing down a completely general theory of scalars, gravity, and gauge fields... Oh, and I should also, sorry, I messed up. What did I call that? This is, I'll call that d hat. So these guys are going to be gauged. This is going to get some gauge connection in it, coming from the gauge fields that live in here. Okay, and right. So if I wrote down just a completely general theory, this, for example, could be a function of all the scalars. It wouldn't have to be just a holomorphic function. This thing could have terms that look like dz, dz, and dz bar, dz bar. It wouldn't have to be dz, dz bar. So supersymmetry, the microphone is really throwing me off. The supersymmetry is somehow restricting the amounts of the couplings that you can have here. Okay, that's the key point. And in particular, it tells you what this metric on this space of fields can look like. So it turns out, supersymmetry imposes that this thing, this Gij, what did I call it, hat, is a Kähler-Hodge metric on X, the field space. So let me tell you what that means. So recall, so Kähler corresponded to a torsion-free UN structure. And remember, that meant that we had a complex structure and a symplectic structure. You'll have to excuse me, I'm going to use MN indices here, even though this space X is not a space-time, okay? Just because I've run out of indices. And this also then had a metric, which you could write as minus omega m p I p n. So how does this work in this language? I've actually already... Ooh. Do I need to do that? Okay. let's do, we've got already these, remember that one thing here was that, okay, so we also had that because it's torsion free, we had that the 9-house tensor vanishes, and we also had the d of omega with 0. And this means that, and it also means that we can have complex coordinates, which are just the ZRs, right? We already have them in this formulation. I've already written things in terms of complex coordinates. Does that make sense? So, in these coordinates, just so in these coordinates, so we can think of the m coordinate as an I and an I bar, right? What we're doing there is we're taking the complexified tangent space and thinking of it as T10 plus T01. And I'm introducing a basis here, which is Zi, and a basis here, which is Z bar, I bar. Is that right? Shall I keep trying? Should I keep going, or should I? No, sorry.
Yesterday we didn't put it properly.
Shall I just try with this?
So I think
Oh,
can hear you.
the students can hear, I think,
And
right?
let's hope that the recording.
And if the recording hears,
Yeah, let's
okay,
hope
we'll try. We'll try. I'm happy. Okay, so I'm thinking of my real coordinate, and I'm splitting it into a complex coordinate and its complex conjugate. Does that make sense? And then in that basis, my I, this component of I is just I, because when I act on vectors in here, it just gives me an I eigenvalue. This component is minus I, because when I act on vectors in here, I get a minus I bar. Sorry, times, then when you're computing times delta ij. This one is minus I times delta I by j bar. And these components are 0. And similarly, I can write the relationship, this relationship between the metric and the two form just becomes omega I j bar is minus I times g I j bar. And omega ij is equal to omega I bar j bar is equal to 0. So I've just written the same structure, but I've used these complex coordinates just to match it to what you've seen before. And actually, locally, the metric can be written using what's called the Kähler potential. So actually, locally, you can always write g ij bar as two derivatives of some function. So I can write it as d by dzi, d by dz bar I bar of some function k of z and z bar. And this is called the Kähler potential. Okay? So because of these conditions, because of this condition basically, it means that I can write this in this way. So that's the Kähler manifold bit, right? A Kähler manifold is something with complex coordinates. It's got a two form and a metric, and it has these relations. Or equivalently, it's a torsion-free UN structure. What about this Hodge business? So yeah. Yep. Yeah. So they're going to be things that have got gauge connections in them as well. So they're not just the ordinary derivatives at the moment. Yeah. Any other? Yes. This is after eliminating auxiliary fields, yes. Why is it called the potential? I mean, potentials are things where derivatives of them gives you the physical thing you're interested in. So I don't know more to say than that. What was was there another question? Yeah. It is. So omega j I bar is equal to I g j I bar. So I'm just telling you that the I j bar component equals that. If I switch them around, sorry. Let's write that complete. The j bar I component would equal that with the opposite sign, which is I g j bar I. So all that relation tells you the I j bar relation. If I did the j bar I relation, there would be a minus sign there. Because as you say, this is symmetric and that's anti-symmetric. Does that make sense? Yeah. No. What you call G here is the same as G. Yes, I'm sorry. No, that's not a stupid question at all. Yes, absolutely. That should be G hat. Yep. Any other? Did I mess up anything else? Okay. So what about this? What about the Kähler-Hodge? What about the Hodge? So the idea there is that this is the same as saying that X is the base of a Kähler cone. So let me tell you what I mean. So let's write down another metric, which is going to have two more directions. So I'll think of it as r squared plus r squared d psi plus a squared plus, and then here, this is the metric that I'm interested in. This is the g hat. So I can think of this as being the coordinates now on here. I have zi, z bar I, and then I sort of have another coordinate, w, which is something like r e to the I psi. It's another complex number. So I've now got a manifold which is two real dimensions larger, one complex dimension larger. And A, this is actually a gauge connection, because this is a U1, this is a phase, right? And if I let psi go to psi plus some alpha, which is a function of z and z bar, then I better let A go to A minus the derivative of that function. Okay, and then this thing won't change. And what we require is that this is also Kähler. So it's complex because I've got complex coordinates. And on here I can write a Kähler form. And the Kähler form that I write looks something like r dr wedge d psi plus a plus r squared times the Kähler form that lives on there. Sorry, I forgot the r squared times this thing. So if you think about this, this looks a bit like a cone. So this is the r and psi directions, and then here I have my this is my x space. So at each point on the cone, I get an x space. But this is not a simple cone because this is twisted as I go around x because of this connection. So strictly speaking, this is a complex line bundle. But just bear with me. So now think we have this form. This is the natural symplectic form on that metric, just using this relation. And so I'm writing it as wedge products. I hope that's okay. Yeah. Yeah, so you can think it's called the base of the cone. So you can think of the cone as almost, it's not really, it's sort of like C times X. So at each point in C, I have an X. At each point in R and psi, I have a space X. Yep. Oh, I should not erase that. Yep.
Do we have to input this moving from our scalar manifold to the smaller as the older manifold in or is something different?
So really what it's doing, it's a fibration. So it's really, I have a map from the cone onto X, and I have a map of the complex numbers into the cone, but it's not really a product. So this is really what's called a line bundle, complex line bundle. But it's really like a U1 bundle, right? With just an extra radial direction. So this thing is just like a U1 bundle over here, and then I put an extra radial direction to make it all cone-like. Sorry, say again? No, so at the moment I haven't told you anything about, so I'm choosing to do it over X, and at the moment I haven't told you anything about A. It could be any kind of fibration. But now what I'm going to do is like, let's look at this Kähler form, this symplectic form. And remember, this has to be closed. So what's that equal to? Well, the exterior derivative of d of r, this term's not going to give me anything. So I'm going to get r dr wedge dA from here. And I'm going to get it with a minus sign. And then on the second term, I'm going to get 2 r dr wedge omega. And then I'm going to get a term that looks like r squared d omega, but that's 0. So for this whole thing to be 0, you see that these terms have to cancel against each other, and I need that omega is actually 1/2 dA. But this is just like a field strength. F for a U1 gauge field. So this is a special case where the symplectic form on the Kähler manifold is actually just the field strength of a U1 gauge field. And that's the same as saying that it's Hodge. So if you have a U1 gauge field, you can take its field strength, that's a nice 2 form. So you could say, oh, well, let's use that as my symplectic form. That's not completely general because that U1 gauge field is quantized. If you integrate its flux, it comes in quanta. So what this does is kind of quantize the symplectic form. It's not completely arbitrary. If you know about de Rham cohomologies, it lives in the integer de Rham cohomology rather than the real de Rham cohomology. So that's the special thing. If I have general Kähler manifolds, I can specialize the Hodge ones, and Hodge ones are where the Kähler form is just a U1 field, is actually a U1 field strength for some line bundle. Is that kind of okay? Yeah. Oh, yeah, no wonder. I meant to call it W, I should call it something else. U. It's a complex coordinate U. I'm just trying to say it's a complex number. It's got nothing to do with anything else. Yeah. No wonder. Sorry. Okay, so I told you what this bit is. So this bit of the action is not an arbitrary metric on the field space, but it has to be a Kähler-Hodge metric. What about these gauge fields? So now let's think about the gauge fields. Okay, so now let's think about the symmetries in gauge fields. So again, we need to do some geometry on this field space X. And in particular, we imagine we have some isometries. Right? So those are coordinate transformations that leave the metric invariant. I can think of them as generated by, yes. Yes. So it's totally true that locally it means I can always write it as dA of something. The question is that a connection on a U1 bundle? And the key point is that, or equivalent, is this the field strength of is omega the field strength of a U1 bundle? And the key point is that for a U1 bundle, if I take any sphere and I integrate the field strength on the sphere, I get an integer, because it just tells me about how much charge is enclosed. So it's a kind of quantization requirement which restricts actually what this could be, because it has to come actually from a U1 bundle. So as I said, this thing, because d omega is closed, you can think of omega, the class of omega, as living in the second cohomology. I don't know if that helps at all, right? This is over the reals. What I'm requiring here is that the class of the omega actually lives in the second cohomology over the integers. So it's like discrete inside here rather than continuous. Yeah, no, that's good. All right, so I now have a set of isometries which are generated by some vectors K, A, M, right? So they're vectors on this field space. And they're isometries, so that tells me that the Lie derivative along K of this metric has to be 0. That's what an isometry is. Is everyone happy with Lie derivatives? And I'm just going to assume you are. But it also has to have that the Lie derivative along K of omega is 0, and the Lie derivative along K of I is 0. So that's a stronger condition. It preserves the whole structure. So it preserves the UN structure. So if you like, think of a sphere, and just the K's are the things that would generate the rotations of the sphere. And then I'm going to have a Lie algebra, which is when I take the Lie bracket between any two of these K's, right? This is as vector fields, the Lie bracket in vector fields. This is going to give me some Lie algebra. For the isometry group. let's call it H. I'll call the isometry group H. Okay, so now I've got these, I can unpack a bit more of what this is, what's going on here. So this gauges the chiral fields. So you get these derivatives, d hat plus z. This looks like dmz plus the way I do it, you do minus a m a times k a as a function of z. So this is like, you're used to writing gauge connections that look like something like dm, dm of phi plus a mu phi or something like that. That's what would happen if this was a nice flat manifold. And this thing would be just generating rotations, phase rotations of that flat space. But now we've got a curved manifold, so this k is playing the role of this phi here, right? This thing that depends on the direction. We would have an I there normally. So that gauges these guys, these z coordinates. And similarly, so I can write my k here. I write my ka as kai d by dzi plus ka I bar d by dz bar I bar. So this is this bit. And similarly, this one will also be gauged. This actually becomes a function just of z, and that just becomes a function just of z bar, but it doesn't matter. And then my field strengths become the usual thing that you would expect. So they become some non-abelian field strength, and the non-abelian nature is controlled by this Lie algebra of these isometries on the space. Okay, I'm making myself tired, so is what I'm saying making sense? Yeah.
In the chiral manifold, we also have the chiral symmetry. We can take the chiral potential and add the
Yes. Yeah.
Can we also gauge this symmetry?
Excellent. So we're going to see that that ends up getting a little bit gauged. So at the moment, you're not seeing anything about that. And let me talk a bit more about it in a moment. Okay, so I've now sort of told you what those d hats are, and I've told you what f is, big F. This little f is just some holomorphic function. As I said, it actually has to satisfy some conditions, but I'm not going to tell you what they are. It's fairly straightforward. But now let me tell you about the v part. So yeah. Yep.
So eventually, when you wrote this d hat, I assume that this d hat is the parameter with respect to the g hat.
Yeah, except they're acting on scalar fields. Oh, yes. So no, it's not that. It's not because these are like coordinates on that space. It's more like dx, the little one form, than it is like yeah, yeah. Any other questions? Okay.
So now we are taking our gauge fields
Yep.
with the gauge field of the isometries of the data space.
They gauge the isometries of this.
We are choosing this. We could also like have two separate sectors.
Yes, so you could say, I'm just going to say there are no isometries or ignore the isometries, just turn it off, nothing will be gauged, and these will all be abelian gauge fields. Yeah. So but the most general thing is you take a Kähler-Hodge manifold and you're allowed to gauge as many of the isometries as you have. But absolutely that's your choice. Yeah. Any other questions? Yeah.
Now the different field strengths. There are from a molecular material those ABC depends on the mass of the material.
Yeah.
Is it still actually a group what we're talking about? If they depend on the fields?
So the isometry group of the X space will be a Lie group. So
For any different value of possible configuration of the CNC bar fields.
yeah, so if I can find an isometry group that actually just preserves the metric in general, it will be locally, it will be a Lie group. Any continuous group that preserves the metric will be a Lie group. Yep. Other questions? Okay, so what about the potential? So now let's talk about the potential. And I'm also going to start talking about the U1R symmetry. So let me tell you what this potential term is. And again, I just have to write down some more things. We have the potential takes the following form. E to the kappa squared k, that's the Kähler potential. This hat metric, ij bar. Then I have some more derivative things. And I've got some new function w. And then I have a term that depends on the real part of FAB. Well, I take the inverse of that matrix and I contract with some things that I call PA, PB. Okay, so now I've got a bunch of more things that I have to explain to you what they are. This is the Kähler potential. This thing is a function of Z, which is called the superpotential. And these things are called D-terms or moment maps, if you're a mathematician. And all these things, so these things are fixed by the KAs, by those isometries. So we've now got this bit, we haven't got any new information, right? The KAs are there, and from the KAs we write down these Ps. Here we've got something new, which is this superpotential, which you can also have in global supersymmetry. Okay. But it's slightly tricky because the superpotential W is really not a function, but it's really a holomorphic section of the cone C. So what do I mean by that? Remember, the cone C sort of had these coordinates which were u, which was r e to the I psi, and zi and z bar I. So what I really need to do is to think of W is like, when it's a section, it's like fixing r and psi as functions of z and z bar. Or really it's like saying u is a function of z and z bar. But this is not a global u. You have to patch it, right? This is patched, not global. Because the psi field was generally a non-trivial U1 bundle. So that means I can't really say that U is a function, just a function of these things. It's actually like saying, as I go around, here's my X. As I go around X, I specify this would be my W as a function of Z. It would be somewhere along the cone, and I have to tell you where I am along the cone as each point as I go around X. So if you recall, we had this metric which looked like dr squared plus r squared d psi plus a squared plus r squared ds squared, or I guess I could write g hat I j bar dz I dz bar j bar. And we had that omega was equal to -1/2 dA. And that actually means we can write A explicitly if we want to in terms of the Kähler potential. And it looks something like I dk by dzi times dzi minus dk by dz bar I bar dz bar I bar. And this is what we call the Kähler connection. So because it was a Kähler-Hodge manifold, there's a natural connection associated to the Kähler form locally. That's the Kähler connection, and I can write it down using the Kähler potential if I want to. So precisely because since W is really a section of the cone, that's why I have this derivative of W is not just dW by dz bar, but it has another term which is just looks like kappa squared dk by dz I times W. And this term is just the Kähler connection. So this is, if I split this into holomorphic and anti-holomorphic bits, it's this bit of the Kähler connection. So this is just telling you that this field is gauged by the Kähler connection. And that's because really it doesn't live as a function on X, but it lives as a section of one of these cones. So you might think that if I want to take a derivative of this, it's just a function, I just take the derivative. But you have to remember that it really transforms. It's not really just a function. It's really transforming with some kind of transformation, which is like the Kähler transformations that you talked about. And so it really picks up a connection term. So you have to write an extra term here, which is the Kähler connection. So I'm just trying to explain to you, again, what each term is and where it comes from geometrically. So the reason you have these capital D's in there is because really things pick up an extra U1 bit from the Kähler connection. Okay. It is. So, and if you look at the holomorphic bit of A, it's just that bit. Right? So that's what's appearing just in here, because I'm just looking at the holomorphic bit. Yep. Yeah.
So you get a little bit lost. You have this action full of components that link in the space of fields.
Yes.
And that structure, if I understood it correctly, is fixed by supersymmetry.
Yes.
So now we are basically looking what supersymmetry is fixing in terms of geometry.
Yes. So I'm trying to explain to you. I haven't told you how it gets fixed by the supersymmetry. You have to believe me, but I'm trying to explain to you what geometry you get in this way. This way.
So
And what all this is. It's all consequences of supersymmetry. Yep. But this term becomes really important. So people who do things like, there's people who try and do early universe cosmology in supersymmetric theories, right? And you've got some scalar fields running around and you're wondering could they be sources of dark energy? Could you have some axionic particle coming from them? And if you're writing down a supersymmetric theory, you better keep track of these guys because they can change what the theory looks like. So they're kind of key when you do phenomenology.
So you have some kind of freedom now in this job.
So the freedom we've had so far is the choice of Kähler-Hodge manifold, which of the isometries we choose to gauge, and this function W. So far, that's the freedom we've got. Are there other questions? Yeah.
Is X compact or?
No, usually it's not compact. Yep. Usually you can run off in field space.
So what's the power of real part of F in the second?
Yeah, this is a bit confusing. So there's the real part of FAB, which is a matrix. So I'm taking the inverse of that matrix, and since it's the inverse, I want to write the indices upstairs. Yeah. Sorry. Okay, so we now understand these terms, and we're left with these terms. So now I have to tell you about moment maps. So remember that we had an isometry which said that LKA of the symplectic form was 0. Now, if you remember your formulae, you can write that as the contraction with Ka d plus d times the contraction with aka of omega. Have people seen that formula before, or is that completely... Not everyone has seen that formula before. I'm not allowed to ask the question who hasn't seen that formula before, because that's the wrong way around to ask it. Let me go with it. D of omega is 0, so this is just d of ik omega. So what I mean is ika of omega is just the contraction, ika m omega mn. It's just got one downstairs index. So I will try and write bigger. Yes, thank you. So if this is 0, then this thing has to be closed. So depending can write bigger. Depending on the topology of the isometry group, yeah, let me just say this and then I'll. Okay, IK means this contraction of the vector into the form. It's called if you've never seen it before, by definition, IKV of a form alpha with M1 up to MP minus 1 is VM alpha M M1 to MP minus 1. So if I've got a form which has P indices on it, anti-symmetrized, IV means take the vector and contract on the first index. So it takes the form down by 1, wherever the question was. Yeah, okay. And it's a famous formula that if you take the Lie derivative of a form, you can write it in this way. But if you like, just believe me that that's equal to this. Ooh, no. Okay. So depending on the topology of the isometry group, you can find the following. So we've got something that's closed. Something that was exact would always be closed. So the question is this exact? And if the topology of the isometry group is okay, then indeed you get something exact. And it's not the obstruction to doing this is pretty weak, so you can almost always do this. One can find functions PA such that IKA into the symplectic form is just D of PA. Okay? Or if I write it in components, KAM omega MN is just dn of some, actually I probably want, what's the conventions? Maybe there's a -2. Yeah, I think I want a -2 here. Is -2 dn of some function. And these things are what are called this PA is a moment map. Yeah.
What if H1 is non-trivial and we have an harmonic form as well?
Say again?
What if H1 is non-trivial?
So actually here it doesn't matter whether H1 is non-trivial. It actually just depends on the topology of the group, strangely. So it doesn't matter what space you're doing it on. It's actually determined by the topology of the group. So you can almost always do this, actually, even if H1 is non-trivial. It's just a particular property that, yeah. Okay, this looks a bit obscure. It's actually something you know really, really well from classical mechanics. And that's why it's called the moment map. So in classical mechanics, right, you introduce your coordinates and the corresponding momentum. And there's actually a natural symplectic form that you write down, which is dqm, which dpm. So you can formulate classical mechanics using Hamiltonian mechanics using a symplectic form like that. And if you have a symmetry in classical mechanics, you know there should be a corresponding conserved momentum. So if I've got a rotation, there should be a corresponding conserved angular momentum. This moment map, this function, is just the conserved momentum corresponding to this symmetry. So it's something you actually know very well. It's just written in a more general way. Right. So we should have a little break in a moment, but let me just write it down. So I think then we've actually got everything. So these moment maps, there's one for, you can think, and there's a moment map for each Ka, right? So you have a whole Lie algebra of Kas, and you get a Lie algebra worth of moment maps, one for each thing in the Lie algebra. And so that's what the last term is. Okay, so that's it. This is the most general, actually not quite most general, but almost most general way of coupling n=1 supergravity to matter. And so any cosmology you want to do, which is supersymmetric, you better do it within this framework. Right? This is the framework that you want to work in. If string theory gives you some supersymmetric theory in 4 dimensions, it's going to be written using this language. Okay, so why don't we stop for 10 minutes? And then we'll come back and I'll quickly tell you about other supergravity theories, because they all have a similar structure. Okay. Should we charge this? Let me just let me say something quickly that I realize we had these D operators, which I said were given by dm, this thing, plus some AMA times KAI. And I said that's a gauging, and I think that looks a little confusing to people. It doesn't look like a gauging that you've seen before, right? So let me just do one tiny little calculation to show you why that's not quite so strange. So suppose I have just a complex field. So it's going to be slightly different, but let's just imagine I got a complex field, and I've got a symmetry e to the I theta z. You're used to saying if I write down a gauging, I should write something like I AMZ dmz bar minus I AMZ bar, or something like that, right? That's this nice linear action here on the fields. But if I think of z as r e to the I phi, this whole thing becomes dmr plus r squared dm phi minus am all squared. So here there's no field multiplying the am, right? But this is just like saying I'm actually on a curved manifold, which is a circle, and I have a symmetry on the circle, which is generated by a killing vector, which is just d by d phi. So this term is exactly like the terms I'm writing here. It's just I'm doing it on a curved space rather than a nice vector space. I don't know if that helps at all. Okay. All right, so we know what all the ingredients are. So I just wanted to say one more thing. So we ignored the fermions, but let's just look at the SUSY variation of the gravitino. So that has the following form. So it's the left bit of the gravitino. It has a projector. And as you might imagine, it has the Levi-Civita connection. But then something else happens. It gets 3/2 I and then some other gauge field, which I'm going to call a hat m times epsilon. So when I didn't have any matter, if I turned off all the gauge fields, the variation of the gravitino would just be the derivative of epsilon. When I turn on the matter fields, I get some extra terms. So I'm doing the variation of the fermion, but keeping only the bosons on the right-hand side. I get an e to the kappa squared k on 2, and I get some superpotential here, and I get a gamma m, and now I get the right projector on epsilon. So I'm not so interested in that term, but I'm interested in this. So what is this a hat m? Well, it turns out it has the following form. So it actually looks just like, it looks like 1 on 6 kappa squared. And then here it actually has the AM, the Kähler potential. Or well, really what I should write, let me write down something slightly. It has, so remember it has the component of the Kähler potential dmzi plus the component of the Kähler potential along I bar dmz bar I bar. So it's picking up bits that look like the Kähler potential, and then it gets another bit by 1/3 kappa squared A m a times the moment maps. Okay, so what am I trying to get at here? If you remember, we had this U1R symmetry that was a phase rotation on the P left. So it was like P left psi m goes to e to the I alpha P left psi m. That was this underlying symmetry of the supersymmetry algebra. The fact that this term is here is telling you that actually this U1R symmetry is getting gauged. It's getting a gauge connection. And the gauge connection comes from the gauge fields that we turn on, but it also gets a contribution from the Kähler connection. So what's happening here is this is getting gauged. So we've got this gauge fields that can all, we've got a gauge symmetry, and the gauge symmetry can act in lots of different places. The gauge symmetry can act on the space X by these isometries, but it can also act on the phase of the gravitino by a U1R symmetry, by a U1R action. So in general, when you gauge the supergravity, when you've got these interactions, gauge interactions, it does a lot of different things. It does stuff on the scalar manifold, but it also actually ends up gauging the fermions by their U1R symmetries, okay? So I just want you to have this idea that in general, it also involves this U1R symmetry, in general breaks the U1R symmetry. Okay? Sorry, I know it's a lot of stuff. All right. Are there any questions about, yes? It's not clear? U1R symmetry is a phase rotation. Isn't that clear? That's obviously right. Where the left part gets multiplied by a phase. Yeah. Sorry. You're very forgiving. Thank you. All right. So if you're happy with that, I'm now going to tell you how every other supergravity works. Just roughly.
Can I choose not to gauge the gravity?
So it's tricky, right? Because this term's sort of always going to be there, because that's the Kähler connection that you can't really get rid of. So technically you can. Well, no, yeah. So yeah, you're a bit stuck. I mean, you could try and you can in fact try and arrange it so that it's cancelled against these terms. So you can set it up so it's not gauged, but in general it's hard. Yeah. Any other questions? All right. So for the rest of today, let me tell you about supergravity quickly, supergravity in diverse dimensions. So I'm just going to give you an idea of what the Sugra plus matter theories look like. Okay. And we'll look at the dimensions between 4 and 11. So in each case, so we have matter multiplets. And I'll label them in the following way. So I'll have things that we call, and I'm also going to have with different n. So I'm also going to allow myself to have different numbers of supersymmetries in each case. So in general, there'll always be things that I call scalar multiplets. And the idea is that these have scalars in them plus spin a half, but nothing else. And then I'll have things that I call vector multiplets. And these will have vector fields plus spin a half. And they might sometimes have scalars. They don't have to have scalars, but depending on the number of supersymmetries, they might have scalars. And then it turns out there's one other thing I need to think about, which are tensor multiplets. And they have something which is a 2 form plus spin a half plus maybe scalars. And these are basically going to appear in d equals 6, the way I'm phrasing it for you. Okay? So we're going to be interested in supergravity. Sometimes the theory might be pure supergravity. So in 11 dimensions, there is no matter you can couple things to. It's just pure supergravity. With lower dimensions and different numbers of n, I might have supergravity, and then I may be able to couple it to some matter. Okay.
Sorry, is a way to see why d equals 6 you have another multiplet?
So the real story is actually it's sort of d equals 6. D equals greater than or equal to 6 in some sense. And that's to do with dualization. So below, in 5 dimensions, if I have something that has like a 2-form degree of freedom, I can always dualize it into something that has like a 1 index. And in 4 dimensions, so yeah, so that's basically why you only see it in 6 and above. And then what happens is that as for the n equal 4 theory, so as for n equal 1, d equals 4, the scalars live on some special geometry, x. So what I mean is, in the action, there's always a term that looks like a half g uv. I'll use indices uv, dm phi u, dm phi v, and this is some kind of metric on x. And depending on the amount of supersymmetry, the geometry of this space gets restricted in different ways. Okay, so we saw that in 4 dimensions, this thing had to be a Kähler-Hodge manifold, a metric on a Kähler-Hodge manifold. In other dimensions, with other amounts of supersymmetry, it becomes something else. So supersymmetry does 2 things. So it restricts the geometry of x. And then also what happens is that and then interactions come from gauging isometries. just as we did before. Yeah.
Instead of contracting the M's and M's in the D's, could we write del n and another metric, a space-time metric?
Oh, put a B here?
No,
Sorry.
the D and the del
Yeah.
in this one. No, which you previously wanted.
Here?
Yeah. Instead of a del n contraction, could we have written a del n and a space-time metric G and H and
Yes. So when I write this, what I really mean is this GMN, where this is the space-time metric. So whenever I write that contraction, I've raised an index using the space-time metric. Yeah.
there is another metric.
Yeah, so there's two metrics. There's the G hat metric, which is the metric on the space of fields, and there's a space-time metric G. Yeah, sorry. Okay, so I'm going to give you some lists of what happens in each case. Okay, so let's start by just saying what the theories are. So this is kind of just what happens with the supersymmetry algebras. So what number of supersymmetries do we have in each dimension? So I'm going to do the usual Clifford algebra thing. So the Clifford algebra, the even Clifford algebra in 10.1 is M32R. And there's only one amount of supersymmetry you can have there. It's just n equal 1. And this has 32 supercharges. And that's the maximum number of supercharges you can have if you don't want to, without having to have higher spin fields. If I look at the even in 9.1, this is M16R plus M16R. So now I have possibilities. I can have n equal 1, 0. I can have n equal 1, 1. Or I can have n equal 2, 0, which is where I put a spinner, just one spinner in there. Or I have a spinner there and a spinner there. Or I have two spinners in there. And these ones will have 16 supercharges. And these two will both have 32 supercharges. This is usually called the n equal 1 theory. This is called type 2A. And this is called type 2B. Then you can keep going. So then in 8.1, it's just M16R. And I can have n equals 1 or 2. And I'll have either 16 or 32 supercharges. In 7.1, it's M H doesn't seem right. I'm worrying now. No, that's C. That's better. Okay, and again, I can have n equals 1 or 2. If n is 1, I have 16 real charges, and if n is 2, I have 32 real charges. And I can also write down what the R symmetry group is going to be. So here it's going to be, there's not going to be any R symmetry here because there's only one n. There's not going to be any R symmetry here because there's only one n. But here in general, the R symmetry is going to be everything is real. So it's going to be SOM plus times SON minus. So because I've got, that's the number of n plus and n minus. And here, it's going to be just SON, because I'm over the real things, and I can have n as, I have to preserve a norm that's over the reals. Here I have to preserve over a norm over the complex numbers, so it's going to be SU, it's going to be UN. So it could be U1 or U2. And if I keep going, if I do the Clifford algebra of 6-1, that's M4 over the quaternions. And now again, I have n is 1 or 2. There are 4 components in each quaternion. So if n is 1, I have 16. And if n is 2, I have 32. And now the group is going to be USP2n. That's the symplectic group, right? That's the group that preserves the quaternions. Then I have the interesting case of the even-Clifford algebra in 5-1, and that looks like M2H times, plus M2H. And so now I have more possibilities. So now I can have n is 1, 0, 1, 1, 2, 0, and I'm just going to do 2, 2. There are in principle theories 4, 0, and 3, 1. And people believe that they're gravitational theories, but we don't know how to write them down properly as gravitational theories. So let me just stick with that. And again, so, this is going to have 8 supercharges, right? Because it's 2, so it's going to be 2 times 4 is 8. And this one's going to have 32 supercharges. And the symmetry group now is going to be USP2m plus times USP2m minus. And then if we go to 4-1, this is M2H, and I have n is 1, 2, 3, 4. And the symmetry group is USP2n. This is the one where people sometimes call this 2, 4, 6, 8, because the number that appears here is 2n. So the minimum supersymmetry in 5 dimensions is sometimes called n equal 1, sometimes it's called n equal 2. And I realized I once wrote 2 papers that were only 18 months apart, and one called it n equal 1 and one called it n equal 2, which is terrible. And then we go all the way down to the Clifford algebra in 3-1, and that's M2C, and we now have n is 1, 2, 3. Well, let me keep it simple. I'm only going to do the powers that, in the same way here I didn't do 2-1. I'm only going to do things that have either got 4, 8, 16, or 32 supersymmetries. There are some supergravities that have things in between, but it just gets too much. So let me just focus on those ones. Okay. And here we're going to have some UNR symmetry. Okay. So that's kind of the list of supergravities that we could have with their number of supersymmetries. So now let me tell you what the theories look like. And I'll do it by the number of supersymmetries. Okay, so let's consider the 32 supercharge theories. So what happens here is that X is a symmetric space. That means it has the form of a group divided by another group, quotient by another group, where H is the maximally compact subgroup of G. And what I'm going to do is in each dimension, I'll tell you what these groups are. So here it's fixed. So it's fixed given the space-time dimension. So each of the, whereas for the n=1 theory that have much less supersymmetry, we were free to choose any Kähler-Hodge manifold. Here in these theories, this space is completely fixed. You have no choice about what it is. Okay. So, oh no. Okay. Yep.
Just, are you requiring that the subgroups that you consider are normal or not? That is this a coset or a quotient space?
It's a quotient space. Yeah, it's not. Yeah, it doesn't give you a new group. It's just that it's a symmetric space, which is just a quotient. Yeah. It's a negatively curved symmetric space. So it's like these are the symmetric spaces where the Einstein tensor is constant. A symmetric space is something where the Einstein tensor is constant. So they satisfy. If you take the derivative of the Einstein tensor, this is 0. PQRS. That's a way of thinking about them locally. So what do we have? So let me give you the list. So if we're in d equals 11, there's no x. There are no scalars. If we're in d equals 10, we could do n is 1, 1. And then the space is actually just the group 0, 1, 1, which is the same as just the real numbers. This is very boring. If we do n to 0, so if this is type 2a, if we do type 2b, we get something slightly more interesting. We get SL2R divided by SO2 as our symmetric space. If you know about type 2a, this is just the dilaton phi. So this is a one-dimensional space, and there's one scalar field, which is the dilaton. This is a two-dimensional space. This is a three-dimensional group. This is a one-dimensional group, so the quotient is a two-dimensional space. This is the axion dilaton, phi and chi. So there's two scalar fields in type 2b. So this is 2a, and this is 2b. And then you can keep going. So we do d equals 9, and we have n equals 2. And you get a space that looks like O, 1, 1 times SL2R mod SO2. And then you can do d equals 8. You again do n equal 2. And you get SL3R mod SO2 times SL2R mod SO2. And then you can do d equals 7, and again n equal 2. And you get SL5R mod SO5. D equals 6. This is n is 2, 2. That's the one with the maximal number of supersymmetries. And you get SO5 mod SO5 times SO5. So these spaces are all sort of analogues of hyperbolic space. This is hyperbolic space. This is two-dimensional hyperbolic space. These are kind of analogues of hyperbolic space. They've all got negative curvature. Yep.
Is that why it's called a symmetric space? Or is that related to it?
Say again?
Or like, is that related to why we call it a symmetric space?
Yeah, so symmetric spaces have a definition, which is that they're the spaces where the Riemann tensor is constant. And if they were to call globally symmetric spaces, then you can always write them as the quotient of one group by another group. And the classic example of that is hyperbolic space. Yep. But here we get some other spaces, and what apparently looks like a fairly random set of groups. So, but let me, in D equals 5, this is N equals 4, and we get the group, okay, now we get the exceptional group E6, modulo USP8. This 6, 6, if you know about, do you know about exceptional groups? The classification of Lie groups, right? Compact Lie groups, they come in families. And there's orthogonal, unitary, and symplectic, and then there's a whole extra set which are the exceptional ones. This 6, 6 just tells me what real form it is. It's like a non-compact form of the group, in the same way that you can do SO31 and SO4. These have the same Lie algebra, complexified Lie algebra. This one's a compact group, this is a non-compact group. This is telling me, actually, this is the most non-compact group. It's called the split form. And then finally, if I do the D equals 4, that's N equal 8 theory, now I get E7, 7 mod SU8. Okay, so this looks like a fairly kind of random set of groups. But what's actually going on, these are all like the exceptional groups. They're all really exceptional groups. So if you know your Dynkin diagrams, I don't know if that means anything to you, but that's the Dynkin diagram of E7. And if I do E6, I cross off that node and I get that Dynkin diagram. So that's E6. I can define something called E5, which is I just cross off the next node. But that's actually the same thing as SO10, as a Lie algebra, which is what appears there. And I could do the next thing, and I could call it E4, and I cross off the next node. But that's actually the same thing as SU5, or equivalently, if I take the non-compact form, that SL5. And I can cross off one more node, and I get that as E3. And that's actually the same as, that's actually isomorphic to SU3 plus SU2, because this is like SU3 and this is like SU2. And that's what that N equal 8 one is. So actually this family is really coming from a family of exceptional groups. And you can get these theories, can get the ungauged theories, by compactifying D equals 11 on on an N torus. So if I take that 11-dimensional theory and I put it on a circle, I get type 2A. If I put it on a 2 torus, I get the D equals 9 theory. If I put it on a 3 torus, and so on. So, and these symmetries actually get related to, so the exceptional groups are related to U-duality groups of string theory on Tn. So I think Mariana talked about T-duality. So you can extend that when you have superstrings to a larger group, which is called U-duality, which includes S-duality, which is this symmetry between strong and weak coupling. And those groups are actually very closely related to these groups. And in fact, they act on these moduli spaces, on these spaces of scalars. Okay? So this sequence that looks a bit crazy is actually not nearly as crazy as maybe looks at first instance. That's the ungauged theory. If you want the gauged theory, you've got to do something much more clever. You've got to somehow find a compactification that turns on this gauging. And that's a much harder problem that we only know how to do in a few cases. Okay.
Can you want develop the isomorphisms to the items? These exceptional and SU1 isomorphisms.
Oh, these isomorphisms. Yes, sorry. So this is SO10. This is SU5. And then here it's SU3 plus SU2. Yeah, sorry. All right, so if you'll indulge me a little bit.
Is there anything to say about the non-maximal cases, or is there just not enough constraints to have any sort of...
Perfect. Let me tell you about the non-maximal. So let's do 16 supercharges. So then if I have d equals 10, for example, I would have the n equals 1, 0 theory, because I just want 16 charges. And here I can couple two vectors. So remember, I had vector multiplets, scalar multiplets, vector multiplets, and tensor multiplets. Here I'm allowed to couple to vector multiplets. And it's a bit boring, so the moduli space here. So again, we have the x is G mod H. And here we just get O11. If I have d equals 9, I have n equal 1, and I can add vectors. And now I get something slightly more interesting. So I get O11 times SO2n mod SO2 times SOn. And this is where I couple to n vector multiplets, right? So I can put in n vector multiplets. And this story goes all the way down to d equals 4, where I have n equals 4 plus n vectors. And there I get let me do d equals 5. D equals 5, there I have n equals